Thousands of stars, planets, and galaxies extend as far as our telescopes can see, with huge stretches beyond them that will remain eternally out of sight. As we break down the fundamentals of this enormous topic, maybe the most important of all, please join us. The cosmos is a huge span of space and time that is densely packed with matter and energy, and it is constantly expanding. The term universe comes from the Latin universus, which means all things, despite the fact that our universe may be only one of many in a so-called multiverse of multiple worlds. Over millions of years, the basic atoms that originated during the early history of our universe have joined together to create numerous galaxies, stars, and solar systems like our own, which are separated by vast distances from one another. At the same time, nuclear processes occurring within stars, or triggered by their violent deaths, have steadily processed the first simple atoms in order to enrich later generations of stars, as well as the space between them, with heavier and more complex elements as part of a continuous cosmic recycling system. By calculating the distances between distant galaxies, astronomers have attempted to place the cosmos on a scale. Searching for so-called standard candles, uncommon objects that are brilliant enough to be seen from great distances, and that follow physical laws that disclose their inherent luminosity or light output, is the most precise method of doing this. Variable stars known as Cepheids are the most suitable standard candles, because the length of their pulsation period corresponds to the average brightness of their stars. The distance between these stars and their host galaxies may be calculated by comparing their theoretical luminosity to their observed brightness on Earth. However, despite the fact that Cepheids are only observable in a small portion of the cosmos, the distance measurements they give are sufficient to disclose a rule of thumb that may be used more broadly. This rule, known as Hubble's law, establishes a relationship between the distance between us and a distant galaxy's rate of movement away from us. It is necessary to use Hubble's law because the cosmos as a whole is expanding, displacing distant galaxies from one another like raisins in a baking pan. Because there is more expanding dough between galaxies, the greater the distance between them, the quicker they travel away from each other. Even more significantly, this expansion distorts light from fast-retreating galaxies, stretching it into longer and redder wavelengths that can be detected on Earth and used as a proxy for actual distance. Overall, the further distant a galaxy is from us, the more redshift in its light there is to be found. Considering that our universe is expanding, it must have been considerably smaller in the past, with stuff packed much closer together in the early cosmos. According to modern measurements of the rate of expansion, known as the Hubble constant, it is approximately 21.5 kilometers, 13.4 miles, per second per million light-years of separation. In other words, galaxies 10 million light-years apart are receding from one another at a rate of approximately 215 kilometers, 134 miles, per second on average. It is possible to pinpoint a period when everything was in the same location by turning the cosmic expansion clock back to zero, which occurred about 13.8 billion years ago and marks the beginning of the universe. Because stuff was more tightly packed together in the early cosmos, it is reasonable to assume that it was also hotter. Temperatures were so hot in the early universe that any matter that created would have disintegrated. In fact, matter and energy were convertible, in accordance with Einstein's famous equation E=mc², which states that matter and energy are interchangeable. As temperatures dropped, however, more complex forms of matter were able to survive for longer periods of time, ultimately creating stable atoms of simple elements like as hydrogen and helium, among others. This is the genesis of the Big Bang hypothesis, which is currently our best explanation for how the universe came into being. The Big Bang, which occurred about 13.8 billion years ago, created the space, time, and energy that comprise our universe. Inflation was a spectacular beginning occurrence that caused all matter to be created in minutes, with the first atoms joining together 380,000 years ago, at which time the universe became transparent. The fact that the speed of light in a vacuum remains constant is an inherent feature of the cosmos. Despite the fact that light travels at a speed of 299,792 kilometers per second, 186,282 miles per second, a speed that seems instantaneous in daily life but is nevertheless limited, the speed of light has significant implications for how we perceive distant space. The farther out we gaze in space, the further removed we are from the present, since light must have left things a long time ago in order to reach our telescopes today. As stars and galaxies evolve, the millions of years elapsed between the arrival of light from nearby galaxies makes little difference. However, as telescopes and detectors have improved, it has become possible to observe objects that are many billions of light years away, so far away that we are actually looking back in time to when they were first forming in the early stages of cosmic history. A barrier surrounding our universe is created by the limited speed of light, which we are unable to go across. We cannot get any information from distant regions of the cosmos that are more than 13.8 billion light-years away, since radiation has only had 13.8 billion years to travel from the Sun to the Earth. Observable universe refers to the enormous bubble of space around the Earth that is defined by this. We are still unable to see objects at the extreme edge of this bubble, because they are too faint and far away for our telescopes to see them. The earliest bright objects to illuminate the newborn cosmos were a group of really enormous stars that existed before the formation of galaxies. It is anticipated that some of these stars may be seen with the deployment of the huge James Webb Space Telescope later this year. A time of about 400 million years after the incandescent Big Bang had cooled into invisibility, during which matter condensed into darkness, is known as the Cosmic Dark Age. It turns out that the darkness at the extreme limit of our visible cosmos is caused by something else as well. Light is stretched and redshifted beyond the limits of visibility as the speed at which distant regions and objects are retreating from us becomes increasingly extreme in all directions. First, light is stretched and redshifted into the infrared part of the spectrum, and then into microwaves, which are radio waves of short wavelength. A weak signal that originates from every point on the planet, the cosmic microwave background, CMB, is the most distant source of all. It is the remnants of radiation that escaped from the incandescent cloud of matter and imprisoned light when the cosmos eventually cooled down enough to become transparent, about 380,000 years after the Big Bang. Thank you for taking the time to watch. In order to show your support for this video, please click on the like button. To view future videos, click on the subscribe button, and if you have anything to say, please leave a comment.